Today we shall be learning about the concept of trees and graphs. And trees and graphs are also a very easy concept to understand, and the code shall also be very simple. You just have to pay close attention to all the code that will be taught to you. Let's talk about the relevance of trees and graphs in computer science. So, as I have already mentioned in our first day of our bootcamp, graphs, all trees are graphs, but all graphs are not trees. So essentially, trees are nothing but a hierarchical structure of graphs. Let me just start sharing my screen. So essentially, all trees are graphs, but all graphs are not trees. And trees are just a hierarchical form of a graph, which means that there will be a parent node and it will have a child node and so on and so on. And a graph is nothing but a collection of vertices, which we call as nodes, and they are all connected to each other with edges. So in our trees, we shall be carrying out the following operations, which is insertion and contain, which finds out if a particular node exists in our tree. And in graph, we shall be having many operations, which is add vertex, add edge, and remove vertex. So let's get started with our introduction to trees. So in our tree, every vertex will be essentially a node. So in our node, as we know, we had a value parameter and a next pointer. So in our tree, we shall be having in the node that we define in our tree, we shall be having two pointers, which is the left pointer and the right pointer. So this is because we shall only be implementing a binary search tree. In a tree, you can have multiple children for a single parent node. You can have 3 children, you can have multiple 100 children. But in our specific course content, we shall be only studying about the binary search tree. And in a binary search tree, there are only 2 children per node, as you can see here. Now, we shall be studying about the concept of full trees, perfect trees, and complete trees. Now, a full tree is when every single node has either 0 children or 2 children. As you can see here, here 4 has 2 children, 3 has 2 children, and 23 has 0 children. So this makes our tree full. And if we add a child to our 7 node, it doesn't remain a full tree anymore. Now, if each and every single level of your nodes of your tree had a child, it would be considered a perfect tree. So here you can see 3 has 2 children and 23 has 2 children. And by the way, 3 and 23 will be considered as sibling to each other because they share the same parent. So in a perfect tree, you can see the entire level is filled. If you remove even one node from here, it's no longer perfect. It's full, but it's not perfect. Is everything clear until now? If there is any doubt, just unmute on mic. And it's also a complete tree. In a complete tree, you can have one child over here, and maybe you can have children in other places as well, and it will still be considered a complete tree. But it's no longer full and perfect. See, you can see that you have added 2 children here, and the level is not entirely filled. So it's not perfect, but it's still complete. As you can see, this is our parent node and these are our child nodes, and they are considered each other's siblings. Now, the tree will follow a hierarchical structure, and you will continue to have more and more children to all of these nodes. And nodes that don't have any children are considered as leaf nodes. Are all these parameters clear until now?
Yes.
Now let's continue with our binary search tree example. In a binary search tree, there will be a specific rule when it comes to assigning children nodes to our parent node. So the value that will be added, the child node that has a lesser value than the parent node, will be going to the left pointer of our tree, and the value that has a greater value than our parent node will be going to the right side of our tree. As you can see, 76 has been added to the right side of our tree, and we'll be taking this 52 node and we'll be appending it to, okay, 52 is not less than, 52 is greater than 47. So we shall check, we shall first of all add it to the right side of our tree, and then we'll check it with this particular child node. And as you can see, 52 is less than 76, so it will become the left side of our left child of our 76 node. Now we take another vertex, which is the 21 node, and since 21 is less than 47, we'll add it to our add it as our left child in our tree. Now we take our 82 vertex, and it's greater than 47, and it's also greater than 76. So it shall become the right child of our 76 node. Now we'll take 18, which is also less than 47. It's also less than 21. So it becomes the left child of our 21 node. Then we take another node, which is the 27 node, and we compare it with our parent, with our root. By the way, this first element is considered as the root of the tree, and we compare our 27 node with the next node, which is this 21 node, and 27 is greater than 21, so it becomes the right child. So as you can see here, all of the values to the right of our root are greater than the root, and all of the values to the left of our root are less than the root. So this is how the concept shall be working. Keeping this particular idea in mind that the left side will have lesser value and the right side will have greater value, it's very essential in carrying out our codes. Now we shall construct our binary search tree. As you can see, our node will be having three data fields, that is the value, the left, and the right parameter. Now we shall be initializing our binary search tree. Now we can initialize it by simply making a class of our node, making an object of our node class, and you can continue to carry out this operation. But in our case, we shall actually not do that. We can simply initialize self.root equal to the new node, and there we have it. We have constructed our first binary search tree. We have initialized our binary search tree. But in our particular case, we shall be taking a different approach. Instead of um, uh, assigning it to a new node, we simply declare self.root to be equal to none. So we'll remove these lines of code and we simply say self.root equal to none. And we shall start initializing our entire binary search tree when we carry out our insertion operation. As you can see here, we have declared self.root to be equal to none. Now, if we run our node class and our binary search tree, then we shall not be getting any value. It will simply print out none. As you can see at the end, none will be printed. Now let's look into our insertion algorithm. We'll first go through the pseudocode of our insertion algorithm and then we'll go through the code. So as I have already mentioned earlier, that the left side of our parent node, of our root node will have lesser values and our right side will have greater values. So first step is to create our new node instance, that is our object from our node class. And then we shall have to start to iterate through our binary search tree and find out the relevant position where we have to append our new node. This is how we shall be carrying out our insertion operation. So for that, we have to firstly check if our new node is less than or greater than the parent node, the self.root node. And if that's the case, first of all, if let's say, for example, our node is lesser than the root, then we'll continue to move to the left, and we'll continue to move to the left until we find none to be yeah, to be our next pointer. And if the pointer is none, then we shall be appending our value into the binary search tree. So as you can see, the pseudocode says if none, insert new node, else move to the next. So it keeps iterating through this subtree, this left subtree, and until the next pointer doesn't become equal to none, it shall continue to traverse through the subtree. It will either go to the left or to the right depending on the value of our new node. Now for iterating through our list, we shall be declaring a temp variable, which will be essentially equal to our self.root. And starting from our root, we shall traverse through our binary search tree. And yeah, one more case, if our binary search tree has not been initialized, then we shall, then obviously we had in our constructor class, we had initialized self.root to be equal to none. And if that's the case, if root equal to none, then our root will be equal to the new node. So our insertion operation will end up initializing our binary search tree if there was no binary search tree initialized in the first place. Otherwise, it will carry out the rest of the steps that are given here. Yeah, and one more thing, if the value that we have to append into our binary search tree is already existing inside our list in our binary search tree, then we shall return false because we won't carry out insertion operation on that node if it's already existing inside our binary search tree. Then we'll simply return false and we'll break out of this loop and our code will stop executing. Is there any doubt in understanding the pseudocode? Okay, let's continue. Now we shall be studying about how to write the code for our insertion. We'll initialize our insert function. It will be taking the value of our new node as its parameter. Now we will be creating an instance of our node class, and as we have written in our pseudocode, if the if self.root itself is equal to none, then we'll simply say self.root equal to. Wait a second, did someone say to repeat? Okay, okay. I will report the pseudocode again, Tanma. So I'll just bring up the entire pseudocode in front of you first. So this is our binary search tree, and we want to insert a new node into our binary search tree. So first of all, we'll have to create an object of our node class. And firstly, we'll be taking in various conditions, various different exceptions and conditions into consideration, which is, for example, if self.root is equal to none, which means you don't have any elements inside your binary search tree. In that case, you'll simply insert root as the first element into your binary search tree. So we will be saying if root equal to none, then root equals to new node. Okay, now if that's not the case, then we'll be moving on to the next line of our code. So for that, we shall declare a temp variable, which will start from our self.root variable. And then we will declare a while loop, which shall continue to which will continue to run until a termination condition is reached. So firstly, if the node that we want to insert in our binary search tree is already existing, for example, if we pass in the value 47 into our insert function, then it will return false because 47 is already in our binary search tree. Okay, if anybody has any doubt until here, you can unmute yourself. Let's continue. So if that's not the case, then we'll be moving on to our next condition, which shall be comparing the value of our new node with the parent node. So for example, if we want to add 27 into our binary search tree, so 47 is greater than 27, so which means 27 will be appended somewhere into the left side of our binary search tree. For that, we'll have to first check the already existing children of our 47 node. If 21 was not here, then we would have simply appended 27 here. But that's not the case. 21 is already a child node of our parent 47. So we shall again take a look at this node. So 21 is now temp. We will be changing its value. We'll go on from temp equal to self dot root to temp equal to self dot left. You shall understand this when you see the code. And since 21 is less than 27, 27 will be added to the right side of our node. Any doubt until here? So this is exactly what our next line here says. If none, insert new node, else move to next. As I said that if 47 didn't have a child, then we would have simply appended 27 into our binary search tree. But since that's not the case, we shall now carry out this while loop on our 21 node. And we shall check if 21 has any children, if 21 is greater than the node that we want to append into our binary search tree. Now we shall be writing out our code for our insert function. So we created a new node, and as I said, if self.root is none, then self.root equal to new node, and we return true. Now we return true just to check if our code is running successfully or not. It's not necessary to return true. And we will be, if that's not the case, then our next code line will be running, which is temp equal to self.root. We shall be declaring a temp variable, which is equal to self.root. And now we have our while loop running with the condition while true. And as I said, if new node is equal to temp, then return false, which means if our new node is already existing somewhere in our binary search tree, then we simply return false. And if that's not the case, then we shall be moving on to the next code lines, which will be checking the children of our parent node, of our temp node. So again, as I said, if new node's value is lesser than the value of our temp variable, then it shall first of all, it would check that if the left child of your temp variable is none or not. Then according to that, it will assign new node into that location. Just take a look at the code again. If new node dot value less than temp dot value, this is our temp, and our new node value was less than our temp. So we shall be essentially going through the left subtree. And since if temp dot left is none, then temp dot left will be equal to new node. And we'll essentially return true just to see if our code is running successfully or not. And if that's not the case, if our temp variable does have children, then we shall be running this temp equal to temp dot left. We'll simply skip this code line and we'll say temp equal to temp dot left. And then again, we will see if this new node dot value is less than the temp dot value or is it greater than the temp dot value. So according to that, our new node will get appended into the left side or the right side of our node. So the value of temp has been updated here. And as you can see, we want to append 18 into our binary search tree. And temp.left is none here in our case. So we can simply append 18 into our location. So let's take another example. If we wanted to append 27 into our binary search tree, then firstly we'll go through our temp and then we'll be checking the value of new node with our root node. And as it is less, we will be going through the left subtree. And as you can see, temp.left for our self.root is not none, which means it has a child, that is our 21 node here. So now temp will be updated to temp.left, as you can see here. And now again, this entire operation will run on our new temp node, which is 21. So again, we'll carry out this comparison with our new temp variable, which is 21. So 27 is greater than 21. So again, which means we'll have to append the value to the right side of our 21 node. So again, we shall be checking if temp.right is none or not. And according to that, we'll again continue to update the temp. If this would be the case if our tree was big, because in our case, temp dot right is equal to none. So we would have been able to append 27 into our binary search tree. Any doubts until here? Let's continue. So this would be the case if the new node value was lesser than the temp value, and otherwise we'll carry out the same code lines on the right side of our binary search tree. If temp.right is none, temp.right equal to new node, return true, and temp equal to temp.left. Let's take a look at the visual one more time so that you'll get an idea. So let's take a look at our entire code. If the node is already existing, then we'll return false, and then we'll start comparing it to all of the nodes in our binary search tree, and then we'll continue to iterate through our tree. We'll traverse through our tree, and then we'll finally append our node into our binary search tree. So we'll have our custom input here with 2 equal to self.true, and 1 will become the left child, and 3 will become the right child. So this is our insert code. Just take a look at the entire code once. As you can see here, just go through the code one more time. If you have any doubts here, you can ask me. Yes, there are no doubts. Okay, so we are going to make our my tree object from our binary search tree class, and then we'll carry out insertion operation by passing value 2 and then 1 and then 3, and then we'll print out the value of the root, which will be 2, then root dot left, which will be 1, and then root dot right, which would be 3. Now, when I run this code myself, I actually try to put in various inputs. I actually change the arrangement of this insert here. So I just said insert 1, 2, and 3. And when I run this exact same code, I actually got an error. Let me just show my PyCharm console and show you exactly what I'm trying to say. Okay, so as you can see, this is our insert function. And I, instead of arranging it in 2, 1, 3 order, I said insert 1, 2, and 3. So I would like to ask you guys, what would happen here? Will our binary search tree be executed in the same exact way as before, or would there be a difference? Does anybody have any idea of what exactly would our binary search tree be like? What would be the what would be our root node? I'll wait for 2 minutes. Anybody has any idea? They can turn on their mic or send it in the chat. 1, exactly. Root value will be 1. Now, what would be root dot left? Exactly. What would be root dot left? Would there be a root dot left? Would would our root node have a left child? Does nobody have an idea of what would happen? Exactly. Exactly. So what would be our right node for our one? It would be 2 because that's the node that we added into our binary search tree right after we added 1. Now with 2, we'll have after we try to insert 3, obviously 3 will become the right child of 2. So I tried to run the same code with the same false. So it gives me error. It says non-time object has no attribute value because obviously there is no left pointer for left child for our root. So it will throw us an error. So let us correct this code. Since one will be the root and two will be the right child of our one, we shall write it down like this. And three will be the right child of two. So if we want to call 2, we'll say mybst.root.write.value. And if we want to call 3, we'll say mybst.root.write.value. It might be a little confusing when I say it, but when you see it, it's easy to understand. And when we run this, we get our answer. Because 3 would be the right child of our right child for our root node, which is 2. Is that clear? I run this code so that you'll get more clarity on this insert function so that you'll understand. If we want to carry out our insertion, all these operations on our binary search tree, we need to have like a proper idea of exactly how these nodes will be appended into our binary search tree. Okay, let's continue then. So we have run our insert operation on our binary search tree. Now we shall be declaring a contains function, and our contains function will take in a value as its parameter, and then it will essentially just go through our binary search tree and check if that value exists somewhere in our binary search tree, and it will return true if it's there in the binary search tree, and it will return false if it does not exist in our search tree. So essentially, if root equal to none, then obviously we return false because our binary search tree is empty. And again, here also we'll declare a temp variable, which shall continue to iterate through our tree until we find out our node. So the logic would essentially not change a lot. It would be similar to our insert operation, temp equal to self.root, and then we move on to the left, and then left. If we want to find out 18, um, then we'll return 18. If we had some other value, let's say 48, or otherwise like 17, then it will continue to move through our left subtree. And since at the end, temp.left for 18 is none, then we can say that this value does not exist in our binary search tree and it will return false. Now we shall be running a while loop, which will run until temp is not equal to none. And then we have our various conditional if our value is less than the left child, otherwise if it's greater than the right child, otherwise if it's equal, we simply return true. Let's write it in our code. If self.root equal to none, then we'll simply return false. This is our first condition handled. And then we'll declare our temp variable to be equal to self.root. Then we'll run our while loop, which will run until temp is not equal to none. If temp becomes equal to none, we'll terminate this while loop and we'll simply return false because at the end of our code, we didn't find any value. So that means this value does not exist inside our node. So we'll continue to iterate through our list. We'll keep on comparing it to the temp variable, which has been updated. We'll keep updating the temp variable according to the value of our new node, as you can see here. And the moment we find our new node inside our binary search tree, will return true, which means the value exists in our tree. Otherwise, we'll not run this entire while loop and simply return false. Let's take a look at the code again. If the value that we want to search for is less than the temp dot value, then we'll go to temp equal to temp dot left. And if it's equal to the value that we want, we'll return true. Otherwise, we'll continue to run these two code conditions. This if and elif statement will continue to run until we reach this else condition. Is that clear until now? So we'll go through our binary search tree, we'll keep on comparing and we'll finally return true. If we wanted to, for example, search for 27, then we'll go temp.left, then temp.right, and we'll return true. Is the code clear until now? Let's take a look at this. Now we shall be running our custom input on it. So this is our binary search tree here. We shall be searching for a value 27 and for a value, let's say 17, for example. So this is our contains method, and we have inserted all of these nodes into our binary search tree. And then we'll carry out our contains function on our object. We'll find out if 27 is there in our binary search tree, and then we'll find out if 17 is there. As you can see, it returned true for 27 and false for 17. Are there any doubts until here? So this was it for trees. Now we shall be moving on to graphs. And graph is also a really important concept that is used in computer science programming. As I have said in our first class, when it comes to the relevance of graphs, our social media networks such as Instagram or LinkedIn, they basically use these graph traversal and tree traversal techniques to just go through your network of connections. And then based on that, they'll tell you who are your mutual friends. And based on your network, they'll also suggest you relevant accounts to follow. So social networking sites also make use of this concept of graphs. And graphs is a concept that is also used in AI. Uh, when you start studying about AI, you'll be using that first search algorithm to find out the optimal solution. So we won't be going deeper into that. Now, a graph essentially consists of vertices, which we actually call as nodes, and they are connected to other nodes using an edge. It's called an edge. Now, you can take a node and you can connect it to as many other nodes as possible. There's no restriction on it. So as you can see, 44 can be connected to 82 as well as 76 and so on and so on. Now, obviously, when we have our graph, we'll also carry out traversal on it. So you could say that if we want to go from 76 to 82, you say it's much easier for me to go from 76 to 82 directly rather than first going to 44 and then going to 82. But this condition would change if you had a weighted graph. For example, Google Maps uses the concept of weighted graphs by saying, for example, from this 76 node to 82 node, there is more traffic, but from 76 to 44 and 44 to 82 wouldn't add up as much traffic. So this would be our optimal solution instead, 76 to 44 to 82, like that. This would be our weighted graph example. Our graph could be weighted or unweighted. There are various types of graphs. There is a weighted graph or an unweighted graph. Otherwise, there could be a unidirectional or a bidirectional graph. For example, on your social media sites, you follow your friend and your friend follows you back. This is called a bidirectional graph. But for example, if you follow a celebrity, but the celebrity wouldn't be following you back. So this is considered as a unidirectional graph. So as I said, essentially all trees are graphs, but all graphs are not trees. Trees are nothing but a hierarchical arrangement of graphs. Now we shall be studying about concept of adjacency matrix and adjacency list. Adjacency matrix is just for us to get an idea of how all these vertices are connected to each other. Firstly, what is a matrix? Can somebody tell me what is a matrix? Just a simple explanation. Just say it in simple language. What is a matrix?
A two-dimensional array.
Yeah, array. Correct. You can say that a matrix is an array. It's a collection of rows and columns. So we shall be initializing an adjacency matrix to understand our concept of graphs, of how all the vertices are connected to each other. So we shall be doing this by declaring 0 or 1. If there is an edge existing between two nodes, in that specific square, we'll say 0, otherwise we'll say 1. And this adjacency matrix will keep on changing for the same graph. If it's like bidirectional, it will be a different graph. If it's unidirectional, it would be a different graph. Not sorry, matrix. And if it's a weighted graph, then also the values in the adjacency matrix would change. So as you can see here, for our A vertex, it is connected to B and E. So for our A column, A doesn't have any connection to itself. It's not reflexive. So we'll say 0 here. And A is connected to B, so we'll say 1 here. A is not connected to C or D, so we write 0 here. And A is connected to E, so we write 1 here. We'll do the same for B. B has a connection with A and C, so in these locations, you'll say 1. And for B is not connected to itself, so we'll say 0. And so on and so on we'll do for all of the vertices. And there we have it. We have our adjacency matrix. Now you might have noticed that along the diagonal you'll find just zeros. And you will also notice that our adjacency matrix is symmetrical. This is only the case when our graph is bidirectional. If our graph was unidirectional, that would have not been the case. If, for example, you said there is a connection from A to B, but no connection from B to A, then it would be written 0 here in this block. Then our matrix would no longer be symmetrical along the diagonal, as you can see here. So these are the different changes that you would see on the same graph, in the same adjacency matrix. You will find different values based on the kind of graph that it is. And if it was a weighted graph, instead of writing 0 and 1, you would have written 0 and the weights. So this is how you declare your adjacency matrix. Now we shall be looking into the adjacency list. Now adjacency matrix is not used in our operations, but adjacency list will be used for our various functions. Now in an adjacency list, we'll be initializing a dictionary and we'll be having key value pairs. And one by one, all of the vertices will become a key, and the values belonging to those keys would be nothing but the vertices with which that key has a connection. As you can see, A has a connection with B and E. So A will be our key, and the value for it will be B and E. And for B, it would be A and C. For C, it would be B and D. For D, it would be C and E. And for E, it would be A and D. So this is nothing but our adjacency list. It's a very simple concept. And we shall be using the adjacency list to carry out our add edge, add vertex, remove edge, and remove vertex operations. So now we shall be looking into our add vertex method. So as you can see here, firstly, whenever we're adding a vertex, we'll simply add our key, add our added vertex as a key into our adjacency list. And there wouldn't be any value pairs initially inside our add vertex method. Whenever we add our edge, that's when we'll start adding vertices into our key value pairs. So at first, this is how our initial self-adjacency list would look like. As you can see here, at first we'll be initializing an empty list into our adjacency list. As you can see here, let's take a proper look at the code. But this will only be carried out if your vertex is already not existing in your adjacency list. That must be clear by now, right? We'll be running through our code like this: if vertex not in self.adjacency list dot keys, which means if in all of the keys of our dictionary, if that particular key is not already there, then we shall be running this code line. We'll simply initialize an empty list to it. And in our add edge function, we shall be adding vertices into our particular key. So these are all of our functions, and we shall simply return a dictionary with first key as A, and it shall be having an initial empty list right as its value. Is this function clear? Are there any doubts? So let's continue. Now we studied our add vertex method. Now we shall be going to our add edge method. So if we are actually going to carry out this operation on bidirectional graphs. So if we add an edge from 1 to 2, we are also going to add an edge from 2 to 1. So essentially, we have to first of all add our vertex 1 into our dictionary and then vertex 2. We shall have to initialize empty list for it, and then we shall have to simply append vertex 2 into vertex 1 list and then vertex 1 into vertex 2 list. As you can see here, at that specific location, we append these vertices into each other. Since this is a bidirectional graph, we shall be carrying out this operation on both of the vertices. And again, we'll have our if conditional here. This condition, these two lines of code will only execute if we already have an existing vertex in our graph. For example, if you said that you have initialized vertex 1 into your graph, and then you say add edge 1, 2, then our code wouldn't run properly. We'll also have to add vertex 1 and then vertex 2, and then you'll make a connection between 1 and 2. And for that, we have this if conditional, which says if v1 in self.adjacency list.keys and v2 in self.adjacency list.keys. And then in our v1 key value, we'll be appending v2. And then in v2 location, we'll be appending v1. And then we'll return true. This is just for the sake of testing out our code. And if that's not the case, if either of one of v1 or v2 is not already in our graph, then we shall return false, which means we cannot carry out our operation. At the end, after we run our code, you shall have seen that 1 has established a connection with 2 and 2 has established a connection with 1. Any doubt in this method? Let's continue. Now we carried out an add vertex method and an add edge method. Now, if we want to carry out removal of edges and vertices, let's look into that. First of all, we shall be looking into our remove edge method. We'll simply first remove the connection between these two, and then we'll look into how to remove the vertices as well. So it's actually very easy to implement remove edge function. So we'll simply say v1 dot remove v2 and v2 dot remove v1 from those specific location. And again, this code line would only run if our vertices are already existing inside our remove edge function. And if that wasn't the case, if if one of the vertices was not existing in our graph, then we would actually be encountering an error, which we'll actually studying about right now. So this is our function here, and then we added vertex A, B, and C, and now we have added an edge between A and B, an edge between B and C, and then an edge between C and A. Now we shall be removing edge A and B. And after we run this method and print out the graph, you can see here that the connection between A and B has been removed. And in no other place you'll see any changes. We see that B and C still have a connection, and C and B still have a connection, and C and A still have a connection. Now let's see what will happen if there is no connection between these two vertices. So for example, if we had our D vertex, and this D vertex is actually not connected to any of the vertices, which means it's not a part of our graph. So in that case, if we run our remove edge method, we will be facing this value error over here. Can somebody tell me how we can combat this error? I think you guys have probably learned about it in Python, and I don't know about Java as of now for freshers. Can somebody tell me how do we handle this error? I'll wait for 2 minutes. You can type your answer, you can unmute. Do you guys recall the, yeah, correct. Try except method. This is how we handle exceptions and errors in our codes. So in order to combat this value error exception here, we shall simply take our code lines, these two code lines, and we'll say try these two code lines, except if value error, if the value is not there, then we shall simply pass from the function, from the code lines, and then we'll simply return false, except value error, and then we just say pass. And then we actually return true false because our method has run successfully. As you can see here, when we try to run our code again, at the end you should have seen that D never had any edges with any of the vertices over here. We had never added any edge with T. So it will simply pass and it will simply print our graph with D initialized with an empty list. So since we can't remove any edge from it, we'll simply print out the graph. So this was our remove edge method. Now we shall be studying about our remove vertex method. So if we want to remove vertex, would we simply just go through our graph and say remove this vertex? Or would we have to do something else before that? Before removing vertex, there is something else we have to do. Can somebody tell me what? If we want to remove our vertex.
Like we have to link the
Yeah,
other
okay.
remain nodes that will remain after that. Like B and C won't be directly connected. So we first have to create a link between B and C before removing the D node.
Um, Actually, Mihir, can you type your answer? I can't hear you properly. It's okay, I'll wait for 2 minutes. Just type your answer. Everybody else also give their answers. What would we have to do before removing our vertex on our graph? Link B and C before removing D node. Oh, so you're saying that we make a new edge if we want to remove our node here. So we'll, okay. Any other answers? Okay, let's continue. So before removing our vertex, first of all, we'll have to remove all of the edges that that particular vertex has with all of the vertices. So in this particular example, we have a graph with vertices A, B, C, D, and you can see all of these connections. And if we want to remove our D node from our graph, we'll have to first get rid of the connections that it has with all of the other vertices, and then we'll just delete our vertex. So we'll delete CD, AD, and BD, and then we'll finally just delete our D vertex. We'll simply get rid of all of these edges, and then we'll get rid of all vertex. So this is our adjacency list, as you can see here. For that, if we want to implement our remove vertex method, we'll have to first take a look at the key value pair of the vertex that we want to remove. So in this adjacency list, for example, we want to get rid of D. So we'll look at this key that is D, and then we'll go through all of the values that are assigned to this key, which means the vertices with which it has a connection. So as you can see, D has a connection with A, B, and C. So our function shall have to check out all of these, the rest of the vertices with which D has a connection, and then go through their values and then get rid of D from them. We'll simply remove D from all of these vertices which have a connection with D. So A will get rid of D, then D will get rid of D, and C will get rid of D. And then at the end, we'll simply delete our D vertex. Is that clear until now? As you can see, we see here that A has a connection with D. Then we'll go through the key value pairs, the value of values that are assigned to A, and we'll just get rid of D from there. And then we'll do the same for B and the same for C, as you can see here. And then we'll simply get rid of our D vertex. Let's write this down in our code. First of all, we have to check if the vertex exists inside our adjacency list in the first place. And now we have run this for loop, which talks about the other vertex. By other vertex, we mean the vertices with which our vertex to be deleted has an edge. Is that clear until now? If you want, I can repeat it. Okay, let's continue. So, as I have mentioned earlier, we'll be going through all of the values that have an edge with our vertex. We'll be going through their lists. As you can see, this other vertex that we have written here, we'll be going through that specific keys list, and then we will remove the vertex located inside the list that we have initialized for our key. So we'll go to this other vertex location, and then we'll remove our vertex from that location. And then we'll simply delete this specific vertex that we want to get rid of. And that's how we got rid of it. Just take a look at the code one more time, and then we'll return true just for the sake of testing out our code. Then we'll return false if our code if the vertex is not inside our graph. So we removed our edges and we also removed our vertex, and this is our new graph. Just take a look at the code again. It's a very simple code again. Just it looks a little complicated, but it's very easy to understand. As you can see, we first checked if our vertex firstly exists inside our graph, and then we go through the rest of the vertices that have a connection with that vertex, and then we go through the those specific keys inside our adjacency list, our dictionary that we have initialized, and then we'll be going through those specific keys, and then we'll be deleting the value from those specific lists. As you can see here, we have added vertex A, B, C, D. Then we have added these edges, which are same as the visual that we showed earlier. And then we will be carrying out a remove vertex operation on our graph. After we remove the vertex, we can see that all of the vertices which had a connection with D have gotten rid of D. And then at the end, our code got rid of D as well. So this was it for graphs and trees. Now, for this last function that I showed, this remove vertex, I actually got a doubt myself, and I tried to run the code by myself, and then I found out that what I was saying had a little bit of an error in it. So we can see our, you guys took a look at the remove vertex code. Just a second, I'll show it one more time. As you can see, this is our code. Now, I was thinking that what if instead of saying self.adjacency list other vertex dot remove vertex, we simply said that we simply call our remove edge method on our remove vertex method. And I thought, would that work? And I tried it out and it wouldn't work. And to understand that, I actually made use of a Python code visualizer. It's an online website where you can visualize your code and then you can understand exactly how your code is getting executed. I'll share that screen and I'll show you what is the error with the concept that I'm talking about. Did anybody else get this doubt? That what if we simply run this remove edge function? Can we get the link for the tool? Of course. This website is called Python Tutor, and I have added our code into this, our entire um, graph class and all the functions relevant to it. We have our add vertex, add edge, and remove vertex. So we have a remove edge function here. And in our remove vertex function, as you can see, we had the code line that said self.adjacency list other vertex dot remove vertex. And I just commented it out and I replaced it with self.remove edge other vertex and vertex. So our code will actually run for 134 steps. We'll just fast forward it and maybe just show you a few initial steps of how it works. As you can see, it first went through our graph class and then it took a look at all the functions. Then our init function and then it returned none and all of that. When you guys have time, you can go through this. So this is how it runs our functions basically, and we can get an idea of exactly how our Python interpreter is interpreting our code line by line. Even the value is returned, return true, return false. So let's get to the ending. Remove vertex. So as you can see, remove vertex took in this vertex parameter. And as you can see, the self parameter, it calls on our adjacency list, self.adjacency list. And these are the values inside our list. It's a little confusing to understand, but when you took a look at it yourself, you guys will understand more clearly. You can copy out the code into this console and run it step by step to visualize how exactly the Python code runs. As you can see, A's vertices are B, C, D. B's vertices are A and D. I mean edges. C has an edge with A and D, and D has an edge with A and B and C. This is the exact same graph that we had seen previously. Now we are running a remove vertex operation. So we'll move on to the next step. It will be iterating through our for loop, and it found out the other vertex, which was A for, see, this is our D key, and this is the values inside it, which is A, B, and C. So our first other vertex would be A. Now we shall be going through it, and then we'll be running this remove edge operation on it, as I have initialized here. I said for other vertex in self.adjacency list at that specific vertex, self.remove edge with that vertex. As you can see here, we run our remove edge operation on A and D, and as we keep moving through, we would have finally gotten rid of that vertex with that connection that A had with D. So now you can see the problem with this way of declaring our function. As you can see here, we still have A, B, C, and D. Okay, no, not yet. We'll keep on going through. Now our other vertex value has become C instead of B, first of all. And then we'll be getting rid of this edge that C and D had with each other. As you can see, this is our new adjacency list. A has a connection with B and C. B still has a connection with A and D. C cut its connection with D, and D now only has a connection with B. Now, when we try to run this code again, this function again on our next vertex, it actually wouldn't run at all. It will simply print the graph and it will simply print the rest of our graph, all of the key value pairs. So at the end, B couldn't get rid of its connection with D. We got rid of D, we got rid of A and D's edge, we got rid of C and D's edge, but we couldn't get rid of B and D's edge. At the end, we even got rid of D, but we couldn't get rid of this edge. Is that clear? So I tried to run the code again so that we can get a proper explanation of how exactly are these functions running. You can also carry out these operations yourself and keep on running your custom inputs on it so that you will get even more proper idea of what exactly is happening with your data structure. So for that, you'll have to practice a lot and then coding will become much more easier for you.